simplified. We then use our definition for G, our Gibbs free energy, and substitute. So here's the definition. We multiply out the terms, a derivative or product, and we make the substitution here, and we end up with the Gibbs free energy, single component, same as the differential change in Gibbs free energy, same as the differential change in chemical potential. And this shows how it changes with pressure and with temperature. So this says for a single component, as the pressure increases, then the chemical potential is going to increase because volume is a positive number. It also says as the temperature increases, the chemical potential decreases. Entropy, also absolute entropy, is a positive number. So let's look at the chemical potential, how it changes with temperature for two phases. So here plotting chemical potential versus temperature for a narrow temperature range. The chemical potential, if the pressure is held constant, then the chemical potential change is just minus S dt. And so you'll notice that the negative slope is larger magnitude for the liquid because the entropy of the liquid is greater than the entropy of the solid. So the idea here is that at lower temperatures, the solid is the stable phase, and therefore drawn as a solid line, because it has a lower chemical potential than the liquid. So here's the liquid chemical potential that existed at that temperature, but the solid is more stable. However, because of relation and can be used to vary the phases you're interested in. The last aspect of chemical potential discussed here is effective concentration. So important, talking about concentration within a phase, this is important. So if we're in the same phase, then a higher concentration, this means a higher chemical potential. And so, for example, suppose you have a gas on the left, and on the right we have a very low concentration of gas, so we have a vacuum. One phase, one component, this is going to be higher chemical potential, this is going to be low chemical potential. Mass transfer then, if there's an opening between these two containers, will go from high chemical potential to low chemical potential. So the chemical potential determination for a mixture is a little more complicated, and we discussed that in a separate screencast. This screencast will discuss chemical potential for a multi-component system, and the importance of chemical potential is that it tells us the direction of mass transfer, because molecules will move from high chemical potential to low chemical potential. Let's look at an example to make this clearer. We start off with a beaker that contains water and iodine. So we've dissolved iodine in water. This mixture is now brown. And what we're going to do is add ether to this mixture. Ether is less dense, so it'll be on the top phase. So I've written equations for chemical potential. This is the chemical potential component I in the mixture. This is the single component chemical potential for that component. And then the activity, this is for liquid phase that we typically end up using activity, it's a mole fraction of the component and the activity coefficient, which depends on what other species are present. If instead we're in gas phase, we typically use fugacity, where our standard state is pure component ideal gas at 1 bar. So this units for fugacity must be in bar for this equation to be meaningful. And if it were an ideal gas mixture, then we can replace the fugacity by the partial pressure. So this is the partial pressure of species I, and you can see the chemical potential depends on the log of the pressure. Now it's worth writing down definition of chemical potential, and that's the partial derivative of the total Gibbs free energy species. So let's look at chemical reactions, and we're going to define chemical potential as 0 for the stable form of the element. Potential scale is arbitrary, so this is like our reference state. The idea is if we had hydrogen gas, standard conditions, or if we had carbon solid, its chemical potential is 0. And then we can look at a chemical reaction. So what I've done is list the reaction from this reference at the beginning of the screencast and list it from the table they have of the chemical potentials for each of these components. So the first thing to note is that these values are all negative, and that's because the species formed, so the elements have chemical potential 0. We go to lower chemical potentials, meaning that we expect the compound to have a lower chemical potential than pure components. And if we add these together, on the left side is minus 12